Okay, so I've been debating this in my mind, how exactly to start the topic of actually computing a matrix inverse. And the book goes through it a particular way, and I think it's good because it motivates why we do what we do. But at the same time, it's not the way that we do things in general. And while I'm talking, let me just entertain you with, smiley faces. Um, that's a girl. So sometimes, now I'm just getting distracted with the faces. Guys winking at you. Okay. Um, so what's the deal? Sometimes I'll illustrate something, but it's not the way that we're going to do it in general. So this is not the way we do things. Let me write this out and just leave it at the top. This is not how we do it. This is just an illustration. It's just motivation. This is the opposite of Montel Jordan. It's not how we do it. Okay. That joke is too old. Let's do it. Okay. So let's let's note the following. Let's say we're looking for the inverse of the matrix. I guess the book does this one. Let me see if I can come up with something else. Let's do 5, 1, 2, 2. Actually, no, let me do it this way. Let's do 1, 2, 2, 5. Whatever. Okay. And let's pretend that it has an inverse. It actually does have an inverse, but let's say that the inverse is A, B, C, D. And so the question is then, well, what, we're assuming that this is equal to the identity matrix. Well, what happens when I multiply these guys out? What do I get? I get 1 times A plus 2 times C. I get 1 times B plus 2 times D. Down here, I get 2 times A plus 5 times C. And down here, I get 2 times B plus 5 times D. And that is equal to 1, 0, 0, 1. So what I actually get here are two systems of linear equalities. Let's notice. I get this is equal to this, and I get that this, two systems of linear equalities. So I have two systems of linear equations. So the first system, the first system is, from these first two rows, I get that A plus 2C, for it to be equal to the identity matrix, it has to be equal to 1, and 2A plus 5C is equal to 0. The other one we get is that B plus 2D is equal to 0, and 2B plus 5D is equal to 1. Now, let's put both of these into augmented matrices. Here I will get 1, 2, 2, 5, 1, 0. Hey, that's fancy. That's precisely the matrix we started off with. And over here we would also get 1, 2, 2, 5. But instead we get 0, 1 right here. Okay. And then we would do row operations and whatever. But look, what I've got going on over here is exactly the same thing that I've got going on over here. So the row operations I would perform here would be exactly the same. The first thing here, I've got a 1 up here, I've got a 1 up here. So what I would do is I would take -2 row 1 and add that to row 2. I would do that over here too, which would give me 1, 2, 1. And that would give me 0. -2 times 2 is -4, plus 5 is 1. And -2 times 1 is -2. And over here, that would give me 1, 2, 0, 1, 1, 0. And then I would take -2 row 2 and add that to row 1, and that would end up with me over here getting 1, 0, 0, 1, and -2 times -2 is 4, plus 1 is 5. And over here, it would be the same exact thing, at least in terms of the operation I would do. I'd have 1, 0, 0, 1. And over here, -2 times 1 is -2, plus 0 is -2. So I would end up with this. So what is this saying? This says that A is equal to 5, C is equal to -2, B is equal to -2, and D is equal to 1, or in other words, the inverse over here is actually equal to it's equal to 5, -2, -2, 1. I encourage you to go ahead and check that out, that's true. It actually checks out. Multiplying both ways, you'll find out that that is completely valid. Okay, so let's get rid of this. But let's note what we really did there, since we did the exact, we did the same row operations on both systems. We really could have combined them into sort of one system at the same time. I could have had 5, 2, 2, 1. No, what did I have? I had 1, 2, 2, 5, 1, 0, 0, 1. If I had done the row operations on this, the left side would have gotten down to 1, 0, 0, 1 as before. This guy, under the row operations, turned into 5 and -2. And this guy under the row operations became -2 and 1. So if I had done the row operations on this augmented matrix, which consisted of the original matrix on the left and the identity on the right, did the row operations to reduce this side, I would be left with the identity matrix. So that general method works. So let's try that out in another case. Let's do something like, let's just do something fairly simple, I guess. Let's do use row operations to find the inverse. Let's start with 0, 1, -1, 0, and let's find its inverse. So we do that by putting, excuse me, this is the inverse we want to find. So this is our matrix. So what we do is we set up 0, 1, -1, 0, and 1, 0, 0, 1. So this is the matrix, let's call it X, that we care about, and this is the identity matrix. Then we do row operations. First, I'm going to swap rows 1 and 2 so that I can get a non-zero guy up here. What that gives me is -1, 0, 0, 1, and 0, 1, 1, 0. Now I want this guy to be 1, so I'm going to take negative row 1 and replace row 1 with that, and I get 1, 0, 0, -1. And down here I get 0, 1, 1, 0. Once I get the identity matrix over here, I stop, And over here, I will get the inverse of the matrix. I will denote it by x to the minus 1. And let's just go ahead and check that this is indeed the inverse. The first row times the first column is 0 times 0 plus 1 times 1. Great. The first row times the second column is 0 times negative 1 plus 1 times 0. That's 0. And the second row times the first column is negative 1 times 0 plus 0 times 1, which is 0. And the second row times the second column is negative 1 times negative 1, which is 1 plus 0 times 0, which is 1. Great, that checks out. And I encourage you to check out that the opposite direction also works. So that's an example for you. And let's do something just a little bit more difficult. Why not? Let's find the inverse of, what do we want to find the inverse of? We'll find the inverse of, let's say, I don't know, 7, 1, 4, 2. Why not? Okay. So the first thing we do is we set up 7, 4, 2, 1, 1, 0, 0, 1. Now I sort of made things a little bit ugly over here because you have to divide by 7 if you want to get a 1 up here. Something else that we can do to make our lives a little bit easier is maybe swap the first 2 rows. This is something that we generally haven't done, although it will make our lives a little bit easier in this case. I get 2, 1, 0, 1, and I get 7, 4, 1, 0. Now I'm going to take the first row and divide it by half, and replace the first row by 1/2 of it, so as to get a 0 right here. Get 1, 1/2, 0, 1/2. Down here I have 7, 4, 1, 0. Now I'm going to take, I want to get rid of this 7 here, I want a 0, so I'll take negative 7 times row 1 and add that to row 2. Replace row 2 with that. So what I get is 1, 1/2, 0, 1/2. And down here, negative 7 times 1 is negative 7 plus 7 is 0. Negative 7/2 plus 4. Well, 4 is 8/2, so this is 1/2. And 0 plus 1 is 1. And negative 7/2 plus 0 is negative 7/2. Now I want a 1 down here, so I'm going to take 2 times row 2 and replace row 2 with that. And I get 1, 1/2, 0, 1, and this is 0, 1/2. Down here I get 2, negative 7. And then finally I'm going to add 1/2, negative 1/2 times row 2 to row 1 to turn this into a 0. And I get 1, 0, 0, 1 over here. Negative 1/2 times 2 is negative 1 plus 0 is negative 1. And negative 1/2 times 7, negative 7 is 7/2. Plus 1/2 is 8/2, which is 4. And that's what I get. So if my original matrix was x, that tells me that my inverse matrix, x inverse, is negative 1, 4, 2, negative 7. And just to be good, just to make sure that we're not messing things up, let's quickly go ahead and check out that that is correct. Okay, so we're going to check this out, and what we get is our original matrix was 7, 4, 2, 1, and we're multiplying that against negative 1, 4, 2, negative 7, and what we get is 7 times negative 1 is negative 7, plus 4 times 2 is 8, which is 1. 7 times 4 plus 4 times negative 7, that's clearly 0. 2 times negative 1 plus 1 times 2, that's also clearly 0. And 2 times 4 is 8, plus 1 times negative 7 is 1, and that's what we hoped for. Done.